Well, let's find out how logs work. So first I'm going to show you something in exponential form. Or just exponent form. You can tell you 10 squared equals 100. So 10 is the base, 2 is the exponent, and I'm not sure what to call 100, so I'll just call it the answer. Okay, so there's the answer we get when we raise 10 to the second power. Now, here is the log form of the same relationship. We say log base 10 of 100 equals 2. So here's the base, but the exponent is now over by itself on the other side of the equation. And this 100 is the input of the log function, which we call the argument of the log. So the argument of the log, its x value, was the original y value of the exponential function. So if we say 10 raised to the second power, if we put, if that is my exponent, now my exponent is over here by itself. So this is really handy if I want to solve something where my variable is in the exponent position. The log form allows me to isolate that variable, which is exactly what I want to do when I'm solving an exponential function. Now, how do we read this? We read this as log base 10 of 100 equals 2. Log base 10. So what I want you to notice, if I put this all on a lined paper, everything is on the same line except for the 10, which is a subscript. It's lower than the rest. What does the 10 tell me? It tells me which log I'm going to use. Now you don't have to write this down, but I just want to write this down as I'm saying this. So if I have a cube root as opposed to a fourth root, the little 3 and the little 4 tell me which root that I'm going to be applying to the number inside. But without a number inside, this doesn't equal anything. It's just telling me what operation I'm going to apply. So this number here tells me which log I'm going to apply to the number 100 in order to get this exponent. So it's the index of the log, or the base of the log. It is not, if we covered up the 100 and just said log base 10 by itself doesn't equal anything. It has to be log base 10 of something. All right, so we're going to now rewrite this with a question mark. So I'm going to take the log form, this form, and I'm going to put it back into exponential form. And notice what's missing on the blank here is the exponent part. So I'm trying to figure out the correct exponent to put on this base in order to get this answer. So I'm saying, in the first one, 3 to what power equals 81? So this is a question mark here. Let's see if I can make that look more like a question mark. 3 to what power equals 81? So if we remember that 81 is 9 times 9, that means it's going to be 3 times 3 times 3 times 3. So 3 to the 4th equals 81. So 3 to the 4th power equals 81. Second one, 3 to what power is equal to 9? 2. 3 squared equals 9. The next one, 3 to the what power equals 3? Well, that's going to be 1. 3 to the first power equals 3. 3 to the what power equals 1? Well, that's going to be 3 to the 0 power. 3 to the what power equals 1 over 3? Well, what exponent makes us take the reciprocal of the base? -1 exponent. Okay, so 3 to the 1/3, 3 to the -1 equals 1/3. 3 to what power is equal to 1 over 27? Well, 1 over 27 is 1 over 3 cubed. What exponent would I have to put on 3 to get 1 over 3 cubed? Well, it would have to be a -3. 3 to the negative 3 is 1 over 3 to the positive 3, or 1 over 27. Now, so I want you to notice here, for when the argument is 1, the exponent will always be 0, no matter what log base we have. So that's kind of an important one to notice. Then we notice as all these positive exponent values have all arguments greater than 1. The negative exponent values have all arguments less than 1. What about an argument of 0 or a negative argument? How do we handle those? So 3 to what power is equal to 0? 3 to what power is equal to negative 3? If you're having trouble thinking what that would be, it's because there is no such thing. There is no value that is no exponent I can put on a positive base and get 0, or I could put on a positive base and get a negative answer. 3 raised to any power is going to be a positive number. It might be bigger than 3, it might be smaller than 3, but it's going to be positive. So both of these are undefined. Technically, G has no answer at all, and H is an imaginary number, but for our purposes in the real number system, we cannot calculate that. So here's what I want you to remember, that the argument of the log is always greater than 0. We can't take the log of a negative number, we can't take the log of 0. This is shown in the log graph. When we did parent functions, hopefully, maybe you remember that the log graph was shaped like this. Notice here that if we look at the domain of the function, or the x values, that x is always greater than 0. Y could be positive, y could be negative, but x is always greater than 0. It doesn't touch the y-axis. There's no part of the graph over here. All right, let's look at this next group. So we're going to go through these doing the same thing, but we have some different bases here. So we have the square root of 2. Well, that's kind of a weird base, but we can do it. The square root of 2 to what power is equal to 2? Would be the square root of 2 squared. Square root of 2 squared is equal to 2. 9 to what power is equal to 1? 0. So remember, whenever this is 1, no matter what the base is, that's going to be 0 here. 5 to what power is equal to 5 to the 7th? Well, it would have to be 7. Notice here that if the base of the log matches the base of the argument, then the two exponents would also have to equal. 4 to what power is equal to 64? Well, 4 times 4 is 16, times another 4 is 64, so it's 4 to the 3rd. 7 to what power is equal to 7? Easy peasy lemon squeezy, that's 1. 6 to what power is 1 over 36? Well, 1 over 36 is 1 over 6 squared, so this would have to be 6 to the negative 2 to get 1 over 6 to the positive 2. 2 to what power gives me 0? Oh, I just got through saying that the argument of the log has to be greater than 0. This is undefined. Okay, so let's look in on the next group. Find x by writing in exponential form. So I'm going to, once again, rewrite this as something raised to a power equals something, but the x now is in different spots. Different pieces of the equation are missing. So x to the first power equals 5. X to the first power equals 5, so x equals 5. Uh-oh, there's no log base here. X isn't the log base here because it's not written as a subscript. There is no log base. What do we do when there's no log base? Well, that's called a common log. A common log is kind of like a square root where we don't put the little 2 there. We just know it's the square root because it's the most common one. Well, the common log is log base 10. So when you have log base 10, you can leave the 10 off and just know it's there. So we could write this then as log base 10 of x equals 0. And notice I didn't put everything in, I didn't put the argument in parentheses on all of these. So if there's just a single number after the log, you can assume that's the argument. Sometimes the parentheses are left off. Just wanted to show you that. So here we can say 10 to the 0 equals x, and 10 to the 0 is 1, so x is 1. Next one, 16 to the 1/2 equals x. 16 to the 1/2 power equals x. We know that 16 to the 1/2 power means the square root of 16, so x equals 4. Next one, x to the negative 2 equals 1/4. X to the negative 2 equals 1 over 4, which is 1 over 2 squared. So if I raise 2 to the negative 2 power, I would get 1 over 2 to the positive 2 power. So x has to be 2. All right, next column. 2 to the 5th equals 32. Or sorry, 2 to the 5th equals x. And then that means x is 32. So 2 to the 5th equals x. X to the 0 equals 1. Well, x could be a lot of different numbers because anything raised to the 0 power equals 1, with one exception. 0 to the 0 is undefined. So x can't be 0. All right. So let's take a look at what about some other numbers. And it turns out if I weren't looking at this as a log base and I just said x to the 0 equals 1, it would be any value of x except for 0, because I could put a negative number raised to the 0 power and I'd still get a positive 1. But log bases are a little bit different. Log bases can't just be any number. So let's take a look at what we can do with log bases. So can a log base be a negative number? So let's look at what happens when we would use a negative number for a log base. So that means negative 4 raised to the y power would equal x. So let's think about negative 4 to the first power. If y was 1, x would be negative 4. So if x is a negative 4, y would be a negative 1. If x were 16, negative 4 squared would be 16, so y would have to be a positive 2. If x is negative 64, y would be 3. So negative 4 to the third is negative 64. So notice that my x's would have to be jumping back and forth from positive numbers to negative numbers, but my y's are all positive. And that's kind of weird looking. If you think about what that graph would look like, it wouldn't look like our normal log curve. And then to throw even more kinks into this, what if x were a number in between, was not a whole number? I'm sorry. What if y was not a whole number? It was a half or a third or a fourth or something. Some of those values of rational exponents can't even give you an x value. So what y was 1/2, x wouldn't even exist because I can't take the square root of negative 4. So a log base can't be negative. So no, a log base cannot be negative. Can a log base equal 0? Well, we just got through saying 0 to the 0 power is impossible. But even not paying attention to that, if I do 0 to the y power, no matter what y is, except for, of course, not being equal to 0, x would be 0. Or if y was a negative number, it would be 1 over 0 to a positive exponent. That would not be allowed. That would be undefined as well. So x would always end up being 0, and y could be any positive number. If x is always the same and y is different, then it's not a function, because that means the x value 0 would have multiple y values. The same thing would happen if the log base was 1. If log base was 1, that would mean 1 to the y power is equal to x, and 1 to any value is going to be x, is going to be equal to 1. So x would always be 1, but y could be any number. That's not a function either. So what do we know about log bases? Log bases must be positive numbers, and it can't equal 1. So when I go back and look at my problem that I was working on, and we say, oh, x could be any number, the correct answer is x could be any possible log base. So x is all possible log bases, which means x is greater than 0 and x is not equal to 1. So any number greater than 0 except 1 would be a correct answer for f. So this is kind of an important thing to remember. I'm going to also star my common log here. Okay, the next one, x to the 1/3 power equals 3. That means that the cube root of x equals 3. And maybe you know off the top of your head what that is. If you don't, you could cube both sides, and you would end up with x equals 3 cubed, or x equals 27. So log base 27 of 3 is equal to 1/3. The next one is log base x minus 1 of 125 is equal to 3. So that means x minus 1 to the 3rd power is equal to 125. Once again, I could do a cube root of both sides, and I would have x minus 1 is the cube root of 125, which is 5, so x is 6. Okay, for the last 3 problems, we're going to go the other direction. For the rest of the page, we've been taking things in log form and writing it in exponent form. Now we're going to take something that is in exponent form and put it back into log form. So I would say log base, well, here's my base is 2, log base 2 of what equals what? Well, the exponent, x, has to be on the other side because a logarithm equals an exponent. So the x has to be here. This is the 7. 2 to the x power equals 7. So if I were solving this equation, this goes back to the problem that I wasn't able to solve on the previous page when we talked about how do you solve an exponential function for x. Well, this is how you do it. When you write the exponential function in log form, then I have log base 2 of 7. I can calculate that on my calculator and figure out what x is. The next one, log base 10 of 7 is equal to x plus 1. Now remember, this is called a common log, so I could also write it like this, just log of 7, and leave the base 10 off, equals x plus 1. And then all I'd have to do to finish solving for x would be log of 7 minus 1 equals x, making sure that the minus 1 is not inside the argument of the log. The last one, e to the x equals 15, I would write this as log base e of 15 equals x. Now, e is a number like pi that has a specific value. It's not a variable. We're going to talk more in coming lessons about log base e, but log base e also has a special name. It's called the natural log. And the natural log is abbreviated ln. Now you might think, why didn't we abbreviate it NL? Well, the person who came up with the idea of natural log was a French mathematician, and the French put their adjectives after their nouns, and they call it log naturel. And so this is abbreviated LN. So we would say ln of 15, natural log of 15 is equal to x. But as I said, we'll talk more about that one later.